So this week's topic is Markov Chain Monte Carlo sampling, and this video is an overview video. Our target, as always, in Bayesian data analysis is going to be the posterior distribution of the parameter conditional upon the data. We saw a couple of ways we could obtain this. One was through conjugate priors, conjugate pairs. Second way was grid approximation. We saw a grid approximation in the water globe tossing experiment, I should say, where we created a very fine grid of theta values from 0 to 1, established our prior, got some data, arrived at our posterior. A key to this was that once we had our joints, our joint probabilities, we summed them up to get the marginal probability of the data, and then divided each one of these joints by the marginal probability of the data to get the goal, the posterior distribution of theta. The difficulty is that when you got a lot of parameters, in practice, determining this is devilishly difficult, and therefore grid approximation is not going to work. However, this marginal probability of the data is a constant, in the sense that it's just a constant that we use to take each one of these things that don't add to 1, convert them to something like this, the posterior distribution, where the probabilities do add to 1. So this thing is a constant. So that means if we look at Bayes' theorem, if this thing is a constant, we can just get rid of it and change the equal sign to a proportionality sign. Now, if that doesn't make sense, think about that if y is proportional, if y is proportional to x, then y is going to be equal to some constant times x. So if we can move in this direction, we can move in the opposite direction. In other words, we can just get rid of the constant and change the equality sign to a proportionality sign. So once we've established this relationship, once we've gotten rid of the denominator, our plan is to now take random samples of these joints, and the relative frequency of these random samples will be the same as the relative frequency associated with the posterior distribution. So how are we going to take random samples from the joints? Well, conceptually, if you think about how you could sample soil from a field, one way would just be to go out, generate at random GPS coordinates and take samples. That's not analogous to what we're going to do. What's analogous to what we're going to do is we're going to go on a random walk. So we're going to start off at some point, and then we're going to have rules for traveling in a particular direction and a particular distance and taking samples. So this is essentially what we're going to do. In terms of the organization of topics for this week, we're going to begin with section 1, which I've shamelessly taken from Kruschke, 2015, that involves a wandering politician. And the wandering politician discovers what's known as the metropolis algorithm, which is just a particular type of Markov Chain Monte Carlo sampling, which is just a particular type of random walk. Just a particular type of random walk. In section 5, the appendix will demonstrate the mathematics that underlies the wandering politician. And what's really important is in section 2, we'll apply the metropolis algorithm to the hand in this experiment. Section 3 will be a bit of a review, and maybe go over a little bit of the math that's in the appendix. And then section 4, for which there won't be a video, will be some terminology. As I go over this, it's really worthwhile noting that this metropolis algorithm, when we apply it to the hand in this experiment, is very much an oversimplification of what's actually going to happen when you have really complicated Bayesian models. However, the plan is that if we can understand how the Metropolis algorithm applies to the Hannon experiment. Next week, when we use run JAGS to write some JAGS code to do Bayesian data analysis through direct coding, we'll be able to see how the Metropolis algorithm enables run JAGS to calculate the posterior distribution.